Hello everybody, this is Carm Killed the Cat, and welcome to your 16th Lua 5.2 tutorial. In this video, we'll be going back to modules, because if you remember from the last video, I couldn't get them to work, so we did weak tables and finalizers instead. But I fixed them, thank you to Zillaresco for telling me how to do it. So now they work, so we'll be going over that in this tutorial. So a module in Lua is kind of like a mix between an include or import from other languages like C++ or Java, and a namespace from C++, C#, F#, or whatever. So it allows you to load a package of external code that can include global variables, functions, pretty much anything you want, any data type in Lua, and it allows you to import that into another file. So rather than just, well, internally it's just running a file, but it's kind of a more disciplined approach, because what a module really is internally is it's a file, and you create a local table within the file. We'll be doing this in a second. And then you put whatever you want in the table, and then at the end of the file you return that table, and then the function we're going to use to import the module will return the table that you returned from this file. I know this is getting kind of confusing. Once we create an example, it'll be a bit easier to understand. So the function we'll be using to import the module returns the table that's returned from the file, and then from then on, in the file that you import the module, you can use any of the global, or not global, but any of the functions, variables, anything that you put in the table that the module is created with. So after that confusing monologue, let's actually get to writing some code to make this seem a bit more understandable. So the first thing we're going to do is we're going to create a very simple module, load it in, use it, and then after that we'll be creating a more complex module and going over some of the better practices to use when creating modules. So to create your first module, you need to create a new Lua file, but there are some complications with Zero Brain Studio. So I've already created the Lua file, but I'm going to kind of walk you through the steps to doing it yourself. So what you want to do is you want to open the File Explorer or Finder if you're using a Mac, and you want to go to the place where you have the Lua file that you're working in right now. So it's called Lua 5.2 tutorial for me. You can see I have it on this path. And in the same directory that you have your original Lua file, you want to create a new one. I called it complex.lua. You can name it whatever you want. I called it complex because that has to do with the module we're going to create at the end of the video. So just call it whatever name you want, and then you have to remember to put the .lua extension at the end, or it won't work. So you can see it says Lua script file here. On Windows, it should say that once you create the file with the .lua extension. Not exactly sure what it'll say on Mac, but it'll be something similar. So make sure it says that, make sure it has .lua at the end, and make sure, this is the most important, that, and also the hardest bug to find, make sure it's in the exact same directory as the original Lua file that you're working in. So you can see these are right next to each other. As long as they're in the same folder, it'll work. So now you can close this, but we're still not quite done. So you'll have the two, or you won't have the two Lua files open yet. You should open the second Lua file the same way that you'd open the first one. And then you want to go to Project, and then Project Directory. And just, you can click on Lua 5.2 tutorial.lua, or whatever you called your original Lua file. And then you can try hitting Set from Current File, and that might work. But I didn't see this button, so what I did, I just clicked Choose, and then pretend I wasn't already here. Then you want to go to the directory that you just created the new Lua file in. So it's right here. And you won't see the two Lua files because they're not folders, and this only shows you folders. But just make sure it's the same directory, and then click Select Folder. So now, let's just, actually we can't do it without writing the module, but for now just trust me, the two files should be able to work together in Zero Brain, and we should be able to create the module in this one, and then load it into this one. Now, if you're not using Zero Brain Studio, you're just using the normal Lua interpreter that came with Lua, then you don't have to do the second part. You just have to create the second Lua file that you want to create the module in. You just have to put that in the same directory as the original Lua file, and the standalone Lua interpreter will know to just search the same directory. But now that we're done with creating the file, let's start creating the module. So, like I said before, a module is just a table that you create in a separate file. Then at the end of that file, you return the table, and then it's imported in from another file. So We'll say capital M equals empty table, and you can name it whatever you want. I just like to use capital M. And then we'll put stuff in the table, so we'll say m.printHello. This module for now is just going to be a few random examples. We'll create an actual example later. Equals function, and this is just going to print hello. Print hello, and then m.pi equals 3.1415. You can put variables in the module, and you can even put another table in it. We can say m.t equals 1, 2, 3. And then at the end of the module, you just return the table. So now we have a completed module here, and we'll just hit Control S to save it. And now, in our original Lua file, we have to load that module in. So we'll say C for complex, just use the name of the file, or the first letter of the name of the file, or pretty much any variable name you want. And then we use our importing function. It's called require. So m equals require, and then you just give the module name as a string to require. So we say complex, and you don't need the .lua at the end. You just write complex because it's obviously going to be a .lua file. So C equals require complex, and now we can access any of the variables within the M table from this C variable right here, which is now set to the M table. So we can say c.printHello. It's not going to autocomplete, but it will work. c.printHello, then we can print c.pi, and for underscore v in pairs, c.t, we can print v, and that'll just print out all the members of this t table in here. So now if we run this, we get hello from the printHello function, 3.1415 from the pi variable, and then 123 from our t table. So we've successfully loaded the module in, and we've called all of the functions and variables within it. So that's how you load and use a basic module. And just as a little bit of a side note, I don't know why the makers of Lua added this, but if you want, you can omit the parentheses around this. It'll work the same way. This makes it kind of look more like an include statement in C++ or C, but I prefer just to use the parentheses around it, just because it kind of fits better with Lua's syntax. There's nothing else in Lua that acts like this, so if you want, omit the parentheses. It makes absolutely no difference, but for the rest of these tutorials, I'll be keeping them in. And again, it works the same way. So now let's move on to some good practices to follow when writing modules. So I purposely made a mistake writing this module, and the mistake is that I made m global. So what's happening when we call this require function is that internally it's just returning the return value of doFile with this function, and doFile just returns the return value of this chunk. So that's a lot of following logic with return values, but basically require is just running this file with doFile and then returning the return of doFile, and therefore the return of this chunk. So we're returning m, but we're also creating this global variable m when we run the file. And if you remember from our environments in running separate files with load and doFile, if we create a global variable, it exists throughout the whole program. So this m variable we create here still exists in this file because we ran the file. And so consequently, we can access the old m table here with the c that we set to the return value of require, but we can also access it from the original m variable. So if we were to say m.printHello, then we get hello twice. So odds are you don't want that, and it's very bad programming practice even if you do. You should try to cloud up the global name, its global scope, I should say, since this is Lua. You should try to cloud up the global scope as little as possible, create as few global variables as possible, and generally just make as many things as you can local. So technically we should call this local, but since this is kind of the main file, we don't really need to. But to get rid of the problem that we've created here, it's pretty simple. We just make m local, and if we save this now, and now we try to call m.printHello, I need parentheses around it, then we get an error, hello, attempt to index global m, a nil value, which basically just means this m doesn't exist in this scope. So by making m local, we've gotten rid of some global scope pollution, which could have been incredibly harmful to the program. I mean, let's just say we were to say m equals 21 up here. Technically, you shouldn't name number variables with capital letters, but just for some reason, say you named some variable m, and then we got rid of this local specifier, and then we tried to print m down here. Now, instead of 21, which you'd expect, you get a table ID. So the m from this file has overridden the m we've created up here. So that's a potential danger if you don't make your module variable local. So always remember to do that. And that's the most major practice that you should always follow. But there are a few other small things that they don't really matter, but it's good to follow them just because it's convention. So the second practice that we're going to go over is that you want to restrict the module's environment as much as possible. So you don't want the module to be able to accidentally access global variables from the main Lua file or any other Lua file that is calling the module. So what we can do is we can set the _env variable to nil, or interestingly, we can also set it to m, the same variable that we create here. And I prefer doing this because it actually allows us to take a little shortcut here, and let me explain why. So by setting the _env table to n, or m, we're really just setting it to an empty table, but it's also just a reference to this m table. So now if we were to create new, what would be global variables in the file, so we can get rid of the m dot here for all of these. So now we're creating what would be global variables that would be accessible from here when we require the module. Now what we're doing is we're pretty much just adding them to the m table, because remember from the last video that any creation of a global variable is implicitly saying _env dot that global variable. And right now, because of this line, the _env table is just a reference to this m table. So now whenever we create what would be a global variable, we're just assigning to the m table. So now, if we save this and run this, we get an error, but the error is that we're attempting to call a global print a nil value. And this can be solved pretty simply in a few ways. The first is to just set a local variable to the _g table, so we'll say g is _g. And then every time we want to call a global function, we have to say g dot and then that. So run this, and now the module works again. We get hello. But this is kind of annoying, so we can take another shortcut here. We can actually set a metatable here. So set metatable, set it the metatable m to table __index equals _g. So now whenever we find, or whenever the module finds some value that doesn't exist, or yeah, pretty much finds anything that doesn't exist from a call like print hello, what the metatable change will do is it will then look in the _g table for that value that can't be found in the m table. So now if we run this, or save this, save it and run this, we get an error, but that's because I forgot the closing parentheses here. So now if we save it and run it, we get hello again, the module still works. And you may be thinking that this kind of defeats the purpose of restricting the global environment, but the problem with the module having access to global variables from other files is that it can sometimes accidentally assign to them. So if we were to create some global variable here, and then for some reason one of these functions changed the global variable with the same name, or any variable with the same name, then the global variable from here could possibly be modified. But if you remember from the metatables tutorial, the underscore index meta field only works for read access. So when we're calling print hello, we're not changing any value here. We're just accessing some value in a table and using it to print a standard out. And also, if we were to use some variable, like I guess if we were to print math.py, so we could also do this, and we get hello, and then longer value of pi than the one that we created here. Then that works too, but what we can't do is we can't assign to global variables. So we can't say math equals 10. And this is allowed. What we're doing here, you should never do, but we're just changing the entire math table that holds math dot, or pretty much any of the math functions in global, so math.py, math.square root, math.pow. We'll go over that in a later video, but all the math functions, we're just setting that to a number 10, so we're losing all those functions. And that's actually not allowed, so if we run this, we get hello, and it did work, but what it's doing is, rather than changing the global math table that would affect the entire program, it's creating a new local variable math in the m table and setting that to 10. So if we were to say print c.math, and we run this, we get 10. So that's kind of confusing, but basically what we're doing is we're allowing access to the global environment, but we're only accessing it in read mode. We can't write to the global environment in the module, we can only read from it. And that's far safer than the default behavior. And there's actually another even safer way to do this, and that's just being explicit. So in this module, the only global function or variable we need is print. So we can say local print equals print. Oops. Equals print. And we do that before we change the underscore env variable. And what we're doing here is we're just saying that we want this global function print, and we don't really need to change the name of it. So we're assigning the global variable print to a new local one, and now we can use that even when we change the underscore env variable, but we can't use any other global function. So now if we were to say print math.py and run it, and run this, it prints hello because we explicitly said that we wanted to be able to use hello in the file, but when we try to call math.abs or math.py, it says the math table is a nil value because we got rid of the old underscore env. And now the only global function we have is the one that we explicitly declared as a local variable. And this method is the one that takes the most code if you have a long module that uses a lot of global functions. But it's also the most explicit and really the best, because there are situations when even reading from the global environment could be harmful to the module. So you really do want to be explicit and just say, I only want these global functions, and just get rid of everything else. I don't want to be able to access it. So when you're writing modules, you should be doing this. But any of the other practices also work for simple modules. But again, if you're doing something complicated, or if you're doing anything, you should use this. It's the best practice. So now that we've gotten all of that out of the way, let's delete all of this. Actually, not this. We can get rid of this for now. And now we're going to create our actual module example. And this example is going to be a module that lets you create and work with complex numbers, so imaginary numbers, so stuff like 4 plus 3i, 3i, 1 plus 6i, anything like that. So really just anything on the complex plane. So what we need to do is we need to create a new function. So we'll say function new, oops. Or we'll actually go with this syntax. We'll say new equals function, no parameters, Actually, we do want parameters. We need, we'll call it real and imaginary. We'll just call it imag. So what this new function is doing is it's creating a new imaginary number that has, and you pass to it the real part of the imaginary number, so it's actually just create an imaginary number that we can use for reference. We'll say 3 plus 7i. So the real part of the imaginary number is this, just the number. So we have the real part of the imaginary number, and then the imaginary part is the coefficient of I. So right here, it's positive 7. We could change it to something like here, where it's 3 minus 5i. Now the imaginary part is negative 5, and so on. So we'll just change this back to positive. So if we wanted to, actually let's just create this. It's a simple function. All we do is return a table, and r equals real. So the table stores the real part, and we'll say I equals imag. So we're just returning a table that has the real part of the complex number and the imaginary part. So now if we wanted to create an imaginary number, we say I. We're just setting a constant here for just this I number here. So I would be new, and it would be 0 for the real part and 1 for the imaginary part, because there is no real part of the imaginary unit I, and the coefficient of I is obviously 1 because it's just I. So now we've created a constant in the module that just represents I itself. So now let's create functions that add and subtract the complex numbers. So we'll say add equals, or function, C1 and C2, and it's going to return a new table that follows the same format. So r equals c1.r plus c2.r, and if you want it to be thorough, you could check to make sure that the tables followed the complex number table format. So just it has an r member and an I member. So r equals c1.r plus c2.r, and I equals c1.i plus c2.i. And this just adds the imaginary numbers. You add the real part, and then you add the imaginary part. And we do pretty much the exact opposite for the subtraction function. So sub equals function c1 and c2. And we return, oh, I don't know why I have an equal sign there. Return r equals c1 minus, or c1.r minus c2.r, and I equals c1.i minus c2.i. And then we end. And now we're just going to create the multiplication function and the conjugate function, or the absolute value function. And you can divide complex numbers, but that is difficult, so we're just going to omit it in this example. We don't really need it. So the multiplication function is mul equals function, again, c1 and c2. And then we return. And this is going to be a bit more complicated, so if you don't know how imaginary numbers work, just trust me, this is how you do it. So r equals c1.r times c2.r minus c1.i times c2.i. And that's the real part. The imaginary part is, we need the I here, I equals c1 dot r times c2 dot I plus c1 dot I times c2 dot r. And if again, if you don't know why this is how you do it, just trust me, it works. And if you don't know how complex number multiplication works, I recommend learning it. It's good for math, and though it doesn't really have to do much with programming, but it is good to know. So if you don't know how this works, I'd recommend figuring it out or just going online and learning why it works. So now we'll create the absolute value function. So abs equals function, and we just take in 1 and end, and we're actually going to need to create or to use a global variable from the global scope in here. So we'll say local. That is not going to work, is it? Actually, yes, it will. Local abs equals math.abs. So now, or it's not math.abs, it's square root that we need. Square root and square root. Actually, we need abs too. Local abs, I haven't worked with complex numbers in a while, sorry, equals math.abs. So what we return here, I'll briefly explain this. The absolute value of a complex number is the distance on the complex plane from 0. So you use the Pythagorean theorem for that. You say the absolute value of some complex number is the absolute value of the square root of the real part squared plus the imaginary part squared. So we could use the POW function here too, but we really don't need to. So we'll return c1.r, or we'll say the square root, or the absolute value of the square root of c1.r times c1.r. It's just shorter to write it this way than to use the math.pow function, plus c1.i times c1.i, and end both those parentheses, and that's how you get the absolute value of a complex number. And we really don't need this function for the we do need this function for the example to show including global functions, but if we didn't have to do that, I probably wouldn't include this because it is a bit complicated. And now, actually, I'm going to skip doing the conjugate of complex numbers. We don't need that. So this is our complete module. So we create our module variable, set it to empty table. Then we include the global functions that we want to be able to use in the module. And then after that, we get rid of all the other global variables and functions and set our environment variable to a reference to our M table. And then from that point onward, anytime we try to assign to a global variable, it assigns to that M table. So we create our function to create a new complex number, creates inside the M table, and then we create all the other functions, and those are all created inside the M table as well, and then we return M. So now, if we go in here, we can get rid of this because these don't exist anymore. We can say C1 equals C.new, and we'll say for the complex, or the real part 2 and imaginary part 5. So this would be 2 plus 5i, and C2 can just be C.i, just C.i. So real part 0, imaginary part 1, and then we'll actually create a C3 too. C.new, that is not new. We'll say 4 and 8. So now we can use our operations here, so we can print, or yeah, we can print, actually it's just easier if we do this. We'll say R1 for result 1 equals C.add C1 and C2, and then we can print R1.r and R1.i, and then we'll say R2 equals C.sub we're just making sure all the functions work. And actually, I'm going to write all the code to test this out because you really don't need to see it. I'm not really demonstrating anything here. So I'm going to write all the code. I'm going to pause the recording, write out all this code, and then I'll show you the result when I'm done. So I'll see you in a second. Alright, so now all the testing code is written out, and I did actually have to change one thing in the module. There was a naming confliction here by calling this ABS and this ABS. So just change the name. I just put an M in front of it for math. You can do whatever you want, but get rid of the naming confliction and also change it right here, and then the module will work just fine. So if we run this, we get 2 and 6, and that's from C1 plus C2. So 2 plus 5i plus 0 plus 1i equals 2 plus 6i. And then we get 2 and 4 for the subtraction. 2 plus 5i minus 0 plus 1i equals 2 plus 4i. It works. And then multiplication is from 2 plus 5i times 4 plus 8i. And that is negative 32 plus 36i. I did the math out. That works. And then R4 is from the absolute value of 2 plus 5i. And I checked that on the calculator. It is 5.385, and then it goes on. So the module works. All the functions work fine. The new function works. All the scoping we did by creating these safer local variables and then getting rid of all the other global variables, that all works fine. And we've created a successful example. So that's all for this video. I'm not sure what we're going to do in the next video, but I'll figure something out by next week. So I'll see you then.